Hi everyone, welcome to AI Crack channel. This is Akash Gangwar and today we'll be studying Indefinite Integrals lecture 2. In last lecture we actually stopped at introduction of substitution. Now we'll be continuing with the discussion of substitutions. Now before moving further, I'll try to give you a particular framework, 2-point framework that would help you implement ideas of substitution in your questions. So the first point should be to make your integral as simple as possible with the help of substitution. It shouldn't be like you have done some kind of partial substitution and it's still looking very complicated and still it's not in the simpler form or the standard form. You should be doing a good substitution that makes your integral very standard and simple. Now, second point, in order to make your substitution very simple and standard, what you have to do, you have to think an optimum substitution that would club maximum number of entities along with dx. So basically, let's say in this question, what we'll do, we'll take x raised power 4 equals to t, and that would give me 4x cube dx equals to dt. So basically, it's covering x cube along with dx. So you have to make these kind of substitutions in all the questions so that it can, club maximum number of entities along with dx. Right, so that would make your substitution even more optimum and standard and make your question even more simpler. Now with all these things being said, let's start with this particular example. Now when I'm looking at this particular question, I would really like 1 plus t square or 1 plus z square, whatever. I would like 1 plus x square, format of 1 plus x square in the denominator, because that would give me the standard integral format of tan inverse x, right? So I would try to do that over here. So that would give me x raised to 4 equals to t, and that would give me, sorry, 4x cube dx equals to dt. So basically x cube dx equals to dt by 3. So we'll replace this one, 1 by 3 times dt divided by 1 plus t square. Now this becomes our standard integral, that is of tan inverse x. So our main motive is to convert the integral into standard integral and revert back again, and plug in the value back again. So that would give me 1 by 3 tan inverse t. Now what was t? X raised power 4. So 1 by 3 tan inverse x raised power 4 plus c, definitely. This should be your answer. Now let us look at this question. Actually, this is integral over here. So this says ln of x plus under root 1 plus x square divided by under root 1 plus x square. Now, looking at this question, my first ideal thought should be to take under root 1 plus x square st, because that would eventually give take dx by under root 1 plus x square in dt. But we are forgetting that it's still not making the entire integral as very simple or very standard, because we still have ln over here. And even if you take this as t, then we have to convert x into some under root format, and that would not make our equation or function very simple, right? So the second thought should be to take the entire numerator as t. So I'll do that. Ln of x plus under root 1 plus x square equals to t. Now let's differentiate it. We'll be getting 1 upon x plus under root 1 plus x square multiplied by chain rule over here. We'll be getting 1 plus 1 upon 2 times under root 1 plus x square multiplied by 2x dx equals to dt. Now let's simplify it further. We'll be getting 2 times 1 plus x square plus 2x divided by 2 times under root 1 plus x square multiplied by x plus under root 1 plus x square dx equals to dt. So we can clearly see that this 2 gets cancelled from here, and this entire gets cancelled with this one. So we eventually got dx divided by under root 1 plus x square equals to dt. We again got the similar kind of format, but it was kind of hidden over here. So basically what we got, integral t dt. So that becomes very simple, t square by 2 plus c. So our t square was this one. So we'll be getting ln of x plus under root 1 plus x square whole square divided by 2 plus c as the answer, right? Now we have seen certain kind of standard formulas, but that was basically reverse of differentiation. But now it's time to see some other different standard formulas with the help of substitution. So you'll have to remember these ones also. Initially, what we learned that were nothing but reverse of differentiation. But over here, you don't see that kind of formulas, but you still have to remember all these formulas. So we'll be doing derivation of these two. You can do the rest. Now let us look at the first derivation, that is integral tan x dx. So what I'll do, I'll write it as sin x dx by cos x. So the obvious substitution over here is to take cos x equals to t. So that would give me minus sin x dx equals to dt. So basically we are getting sin x dx equals to minus dt. So I'll plug in over here. What I'll get, integral minus of dt divided by t. So this is nothing but minus ln mod t plus c. Why I've kept mod t over here? Because cos x can take negative values as well. But in actually in ln we cannot take negative values, right? So that is why we have to keep mod t over here because of the domain constraints. So now plugging back t once again over here. So that would give minus of ln cos x plus c. So I'll take this over here, basically cos x mod cos x raised to power minus 1. So that would give me ln sec x plus c. So this you should be remembering. Now let's look at second derivation, that is integral of sec x dx. Now what I'll be doing some manipulation over here. I'll try to multiply it with sec x plus tan x in both numerator and denominator. But just once think about this, why I would do that, because I cannot directly integrate sec x and I cannot integrate directly tan x in this tan format. I can now, but initially in the basic elementary process I cannot do integral tan x, but I definitely know sec x tan x and sec square x. So that's why this particular thought came into my mind, to multiply sec x plus tan x in the numerator and denominator. Now I can take this as the t part. So I can substitute this one with t. So sec x plus tan x equals to t. So that would give me sec x tan x plus sec square x dx equals to dt. And that is written in the top. So basically we are getting integral dt by t. Again that gives me ln t mod t plus c. Now plug in back t once again over here. I would get ln sec x plus tan x plus c. This should be remembered. Now you could see that we have written this in this particular format. Let's try to write this one as well. So we have over here sec x plus tan x. Let's try to convert this into sin and cos. So that would give me 1 plus sin x divided by cos x. Right. Now whenever you see 1 plus sin x, this should automatically trigger one thought that this is nothing but 1 is nothing but sin square x by 2 cos plus cos square x by 2, and sin x is nothing but 2 sin x by 2 cos x by 2. Basic identities, right? So this should be nothing but sin x by 2 plus cos x by 2 whole square divided by cos x. So this is nothing but cos x, cos into 2 times x by 2, and that is nothing but cos square x by 2 minus sin square x by 2. So that would give me s plus c whole square in the top, and in the denominator we'll be getting c minus s and c plus s. So this cancels out. So that would give me cos x by 2 plus sin x by 2. Now cos x by 2 plus sin x by 2 is nothing but sine of x plus pi by 4 multiplied by root 2, and divide by same with this one, cos x by 2 minus sin x by 2 is nothing but root 2 times cos of x plus pi by 4. This gets cancelled out and this becomes tan of x plus pi by 4, right? Now let's take few examples. Integral cos cube x under root sin x dx. Now the first thought should be to take sin x as t, but again that would not remove under root completely. So my main motive is to make the integrals simpler as well, right? So what I'll do, I'll take sin x equals to t square. So that would give me cos x dx equals to 2t dt. Now let's try to plug it over here. So this would become cos square x times under root t square times cos x dx. So this is nothing but 2t dt. What I did, I took one cos from here and clubbed in over here. So now cos square is 1 minus sine square and sin x is t square. So this would give me 1 minus t raised power 4 multiplied by t multiplied by 2t dt. Integral of that would give me, I'll take 2 as common over here, and that would give me t square minus t raised power 6 dt. Now this becomes very simple. You can integrate it further. Now let's look at this example. Integral of 1 upon x raised power half plus x power 1 by 3 dx. Now our first motive is to make the integrals simpler. So because of that, the first thought that comes to my mind is take x equals to t raised power 6. That would give me dx equals to 6 t raised power 5 dt. Now let's write it back. So this would give me 6 times t raised power 5 dt divided by t square plus t cube, right? T square would get cancelled out. So that would give me 6 times integral of t cube dt divided by 1 plus t. Now we don't have 1 plus t square over here, but 1 plus t over here. Now to convert 1 plus t in the numerator, what I'll do, I'll just add 1 and minus over and add and subtract 1. So that would give me 6 times t cube plus 1 minus 1 dt divided by 1 plus t. Why I clubbed t cube with plus 1 and not with minus 1? Because this will give me 1 plus t and 1 plus t square minus t, right? But if I have done with t cube minus 1, then I would have got t minus 1, and that doesn't cancels out. So that's why I took plus 1 over here and minus 1 over here. So this would give me 6 times, and this becomes t plus 1 t square plus 1 plus not plus minus t divided by 1 plus t and minus 1 upon 1 plus t integral dt. So this is the standard format, right? This can be done easily. This is ln, and this gets cancelled down, and this again becomes very standard algebraic format, right? So this is how you have to approach this problem. Now let's look at one last problem of today's lecture. Integral tan x, tan 2x, tan 3x dx. Now we'll have to go back to trigonometry. What we used to do earlier is we used to convert products into summations and vice versa according to the situation. And over here, we definitely prefer summations over products, right? We don't really know how to solve these products, but we definitely know how to solve them separately. So what I'll try to do, I'll try to convert this into summation. So the first idea that comes to my mind after looking at this is I'll try to write this as summation of this. Tan of 3x would be tan of 2x plus x, and that would be tan 2x plus tan x divided by 1 plus tan x dot tan 2x, right? Now I'll cross multiply. So basically I'll get tan 3x plus tan 3x dot tan x dot tan 2x equals to tan 2x plus tan x. So basically we have got tan x dot tan 2x dot tan 3x equals to tan 2x plus tan x minus tan 3x. So this product is nothing but this one. Now this becomes very standard, right? So this becomes integral tan 2x plus tan x minus tan 3x dx. Now this is what we derived earlier. This is nothing but 1 by 2 times ln sec of 2x plus c. This is ln sec x, and this is 1 by minus 1 by 3 times ln tan 3x plus c. Right? So this becomes in the standard format. Oh, we have one more question left. Let's see this one. Dx divided by cos x minus sin x. Now we just saw a little earlier that whenever you see this kind of format, you have to convert this into singular cos or sine, right? So cos x minus sin x is nothing but cos of x plus pi by 4. So this becomes integral dx divided by, so basically sec of x plus pi by 4 dx. This becomes this one, and we know integral of this one, right? So this becomes into the standard format. So whenever you see this kind of format, cos x plus sin x minus sin x minus cos x, sin x plus cos x, you just have to convert them into singular cos or sine and then just do this standard integral. Now, if you remember that we studied these standard substitutions in the derivative lectures as well, right? So the basic idea is to, get rid of the roots part. So over here, what I'll do, I'll take x equals to a sine theta. So that would make it a square times 1 minus sine square theta. That would eventually give me a square cos square theta, and that helps me getting rid of the root. Or you can do a cos theta as well. Both ways it's fine. Similarly, over here you can take either a tan theta or a cot theta. That is fine. Over here, you can take a sec theta or a cosec theta. That is again fine. But over here, it becomes a little tricky. If you take a square cos 2 theta, then it will be much simpler as compared to a square sin 2 theta. Let me show you how. So let's take the first case, a square cos 2 theta. So that would give me a square minus, sorry, a square minus a square cos 2 theta and a square plus a square cos 2 theta. So this eventually becomes under root of a comes out, not a is not coming out, a just cancels out, and this is nothing but 1 minus cos 2 theta and 1 plus cos 2 theta. And this is a very standard format, right? 1 minus cos 2 theta is 2 sin square theta, and this is 2 cos square theta. So 2 gets cancelled out. This become sin theta by cos theta. So this becomes tan theta, right? Now if I take sin 2 theta over here, what I'll get a square times 1 minus sine 2 theta divided by a square times 1 plus sine 2 theta. Now this gets cancelled out. I can definitely solve this one, but it would become much more complicated. 1 minus sine 2 theta would become sine theta minus cos theta whole square. And this would become sine theta plus cos theta whole square. It's written 1 plus sine 2 theta is nothing but sine theta plus cos theta whole square, and 1 minus sine 2 theta is nothing but sine theta minus cos theta whole square. Now I have to convert this into singular sine or cos, right? So this would become cos of x plus pi by 4 whole square, and this cos square basically over here, and this would become sine of x plus pi by 4 whole square. So eventually you'll get it over here, but that becomes much more complicated as compared to this one. That was pretty much straightforward. So you don't really want to take a square sine 2 theta over here, but you would prefer a square cos 2 theta over here. In other three cases, you can do the interchanging, but not here. Now these are some standard integrals derived from the standard substitutions. So the first three are actually kind of intuitive. If you just plug in 1 over here in place of a, if you just plug in 1 over here, that is nothing but derivative of sine inverse x. If you plug in 1 over here, that is nothing but integral of derivative of tan inverse x. And if you plug in 1 over here, that is nothing but derivative of sec inverse x, right? But these two are not very intuitive and you have to derive it. So you can derive it with the help of same kind of substitutions. You can do it by yourself, and we'll study about these standard integrals in the next lecture. So today's lecture was still here only, and in the upcoming lectures we'll be talking about some more formats of substitutions, some more questions over there, and we'll be introducing by parts and a little bit of partial fractions, and that would end the indefinite integral parts. So let's meet tomorrow. Thanks for watching.